Hey everybody, we're here talking about Unit 2, Lesson 2, power functions. Let's get into it. Any function that can be written in the form y equals some constant k times x to the a power, where k and a are non-zero constants, is a power function. The constant a is the power or the exponent, and k is the constant of proportion, or a constant of what we call variation. We say that f of x varies as the 8th power of x, or f of x is proportional to the 8th power of x. So here are some common formulas from geometry and science. We've seen these before. Circumference, c equals 2 times pi times r. Because that r is our variable and it has an invisible 1 exponent, we call this a power of 1. And the constant of variation is what's being multiplied in front. Basically, that coefficient is 2 pi. The area of a circle, we see that it has a power of 2, so the power is 2, and the constant in front is just pi. For the force of gravity, we see that it has a 2 in the denominator, which means that this is equivalent to k times d to the negative 2 power. So this tells me that negative 2 is its power, and its constant is this k in front. So we say that constant is k. And then Boyle's law says v equals k over p. K is a constant, okay, but this p in the denominator is like saying k times p to the negative 1. So its power is negative 1, and its constant is k, being multiplied in front. So as we write and analyze these power functions, for example, in the formula d equals 1/2 g times t squared, it's to state the power and the constant of variation. So the power is pretty simple. It's going to be the exponent on the variable, which we know is 2, and its constant of variation is the number or the coefficient in front. So it's going to be 1/2 times g, where g is the force of gravity, which is also a constant. So for example, number 2, it says, write the statement as a power function. Use k as the constant of variation. It says the area A of an equilateral triangle varies directly as the square of the length s. So we're going to say the area A in terms of the length s. So we're going to say the area in terms of s, or A of s, equals, and because it has a varies directly, we know this means multiply. So we're going to multiply some constant, whatever that constant is, it could even be 1, times s squared. Okay, so number 3, it says state the power and constant variation for the function below, graph it, and analyze it. So if I see that we have 2 times the 4th root of x, this is equivalent to 2 times x to the 1/4. Because remember, if this has an x, this is a power of 1. And anytime you have a root, that is our denominator of a fractional exponent. So we know that the power of this is 1/4, that the constant of this is 2. So we also know that if I'm going to graph this, it looks something like this, okay, where at 2, if I plug this in, the 4th root of 2 times 2 is some value, and we know like the 4th root of 16 is 2, times 2 is times 4, so we go, this is a 4, right? So here's what we know. We can say that the domain starts at 0 and goes to positive infinity. So we say the domain goes from 0 to infinity. We also see that for the range, it starts at 0 and it goes up. So we're going to say that the range also starts at 0, goes to infinity. Here's what we know about it. It's increasing. We can see that. It's continuous. Its absolute minimum, or its absolute lowest value, is 0 when x also equals 0. And it's bounded below, meaning it has a bound below it. Okay, let's talk about monomial functions and their graphs. So any function that can be written as f of x equals k, or f of x equals k times x to the n, where k is the constant and n is a positive integer, is called a monomial function. Okay, and that's because it only has one term. For any power, k times x to the a, one of the following three things happens when x is less than 0. So keep in mind, when x is less than 0, that tells us a couple different things. Number one, the one thing that can happen is f could be undefined for when x is less than 0, depending on the function. F could be an even function. Also, f could be an odd function. So for example, if we have y equals negative x to the 1.5 power and x is greater than 1, then we should say, then we know a has to be greater than 1, where a is that power. If we have an example like y equals x times 0.4 power, this tells me that a is greater than, or should be less than 1, but also greater than 0. If you have the example y equals 2 times x to the negative 3, we also say here that a could be less than 0. Okay, so we're looking at these graphs. I know on your graph it doesn't show color, it shows only black and white, so go ahead and feel free to highlight these as you can. Remember that this is green here, so here's our green functions. This one is red, and this one is blue. So go ahead and color or notate that so you can really see it on your graph. Okay, it says the forms of graphs below are the four shapes that are possible for a general power function of the form f of x equals k times x to the a power for when x is greater than or equal to 0. So for these ones, we see this one in blue is y equals x to the 0.4 power. And this one here in green is y equals 2 times x to the negative 3rd power. And we see this one in red down here is y equals negative x to the 1.5 power. Okay, so for example number 4, it says graphing power functions. It says describe how to obtain the graph of f of x equals negative 2 times x to the power of 6 from the graph of x equals to the power of 6, or x equals g of x equals x to the 6. State whether the function's even or odd, sketch the graph by hand, and support your answer with the graph. So number 1, let's go ahead and graph what that x to the 6 would look like. And now x to the 6 looks basically like a kind of a parabola, but it's got a little bit of a kind of wider base to it. So that's our x to the 6. So number 1, in order to change this from its power or from its parent function, we know that this negative in front is a vertical reflection over the x-axis. Okay, this 2 in front is a vertical stretch by a factor of 2. We also know that f of x, so part 3, that f of x is even, and that's because it's x to the 6th. We can prove it by saying, hey, if we plug in f of negative x, we get negative 2 times negative x to the 6th, which is equivalent to negative 2x to the 6, which is the same as f of x. It tells me that it's an even function. And we can see what some of those graphs are if I plug in some specific values of x. So like when x is negative 1, 0, 1, and 2. If I plug this in, negative 1 to the 6 is positive 1 times negative 2 is negative 2. 0 to the 6 is 0 times negative 2 is 0. 1 to the 6 is 1 times negative 2 is negative 2. And 2 to the 6th is 64 times negative 2 is negative 128. So if I kind of sketch that, we see that it's a vertical reflection, and it's by a vertical factor of 2, which will make it look a little bit skinnier. It'll be 2 times taller upside down. Let's sketch 3x to the third. State whether the function's even, odd, the end behavior, and the leading coefficient. So remember, looking at this, we know g of x is odd because it has the power of 3. We can also state by its end behavior, it's a positive odd, so it's going to go up to the right and down to the left. So we know the limit as x approaches negative infinity, f of x is going to approach also negative infinity, and the limit as x approaches infinity, f of x is going to go up to positive infinity. We also know that the leading coefficient is 3. So if I'm looking at that, it's going to look something like this, where when it bends, it'll be at y equals 3. Let's talk about applying end behavior. We've talked about this in Unit 1, but here it comes again. So we know when there's even positive, we know that one side goes up to the right and the other goes also up. So as x approaches negative infinity, it goes up to positive infinity. That's on the left side. And as x approaches positive infinity, it also approaches positive infinity. That's on the right side. If it's a power, we already know this, that as it's positive and odd, remember anything on the right side that's positive always ends upwards. So as x approaches in positive infinity, f of x also approaches infinity. And on the left side, as x approaches negative infinity, it's going the opposite direction because it's odd, so therefore it's negative infinity. And in order to have a negative constant, we also know anything that's negative goes to the right downwards. So as x approaches positive infinity to the right, it goes downwards to negative infinity. And anything that's even, they will match. So it's as x approaches negative infinity to the left, it's matching its f of x behavior, which is also negative infinity. And lastly, if it's negative and odd, we know negative always goes downward. So as x approaches positive infinity to the right, it's going, f of x is going downward, so negative infinity. And as x approaches negative infinity to the left, it's going the opposite direction, which is going to be positive infinity. We're going to do this matching in class, so that's it for now.